pop overseas and try to get some European input on some of the exciting things that have been happening. OGC will be represented here by our first speaker, Josh Lieberman, and as we just mentioned, OGC has also been a major player on this side, maybe at a more global level and a more broad level than some of the dig stuff that we just saw.
Okay, thank you so much for inviting me to talk about MUDDI, and I wanted to talk about specifically the role that it plays, because whenever you say, well, I'm going to have a particular domain of data, the implication is that we're trying to take over the world and displace all the other models and communities, and this is very much not the case. So let's talk about this. And this is in relation to an effort that started almost 2 years ago, where OGC, with assistance from the Fund for the City of New York, embarked on a concept development study. We said we know a lot about above ground infrastructure, and we have a lot of geospatial models for those. We know very little about what goes on underground, and we have few models which are specific to that, which have the information to deal with where things are located absolutely and in relation to one another. So the idea was to work towards an integration and harmonization model. And so this is not to replace other models that are used in certain communities, but to look at use cases that really require integration. So being able to look at data for all aspects of the underground at once, and harmonization. So understanding what concepts are in common and that allow integration, even from very different perspectives, whether that's building or modeling or operations and so on. So we'll look at integration, harmonization, what those use cases are, what data models result, and specifically what design patterns enable that. Then a quick look at data quality and the visual part. All of this is not very useful if we can't communicate visually the result of it. So integration needs. Some of these are pretty obvious, others not much so. So the kind of primary use is, if we dig here, do we hit something? And it doesn't matter that, well, I'm from the gas company. If you hit water pipe, I don't care. A hit is a hit. It causes all sorts of effects no matter what the infrastructure is. And a disaster is a disaster. So flooding affects whatever is there. An explosion affects whatever is there. The systems we don't know about still blow up, and especially the ones that we don't understand and whose interdependencies we don't understand really do blow up, increases the risks. So these utilities increasingly do not stand alone. They have both spatial and functional dependencies. Another aspect of integration is combining the structures and the environment. So although it may appear so in some visualizations, the ground is not empty. The environment, what supports the pipes, what affects the pipes, what causes the cables to break, matters. And this is only getting worse as the concentration of infrastructure in the underground increases. One system overlaid on another, running alongside another, intertwined, and crossing, so that the really who owns parts of the underground become important as issues of occupation and resolving occupational disputes. Conflicts need to be resolved. The other thing is that there is often a perception that what you see on the surface is disconnected from what's going on underneath. And of course, we know intellectually that's the case, but being able to show it and therefore show the dependencies, well, that valve actually is connected to a pipe underneath. It isn't just sitting there on the surface. So many reasons why integration is important. And the rest of the underground, as we said, not only is critically important for supporting and affecting it, but as opposed to infrastructure which tries not to run into each other, the aspects of the underground environment are very much overlapping, different perspectives overlapping in space and time. So the geology is happening in the same place as the hydrogeology and the geochemistry. Even though those are different perspectives, the need to integrate over time and space and then distinguish those is really important. That leads to a great variety of conflicting interests, features of interest for observations that are made. So harmonization. Well, harmonization is required in order to have an integration that makes any sense. So they're very practical ones. We harmonize so that we can have a common ground that reduces the exchange and transformation problem. For integration, we need to know what can be integrated and what not. It goes from, okay, those are in meters, these are in feet, to much more involved difficulties of, are we talking about the same thing? Uh, Being able to do that on a sustainable basis is very important in current, being able to continue those integrations rather than doing it once and then losing track. Uh, in order to have an integration that's usable, awareness of quality and completeness so that data are comparable and so that that conformance to standards of quality and completeness can be tested. The work of harmonization is just the sitting at the table and trying to compare. Well, when I talk about this, is that really what you're talking about? That practically, there are standardization mechanisms. I provide an example from an ongoing process of finding the overlap between city GML industry foundation classes and land infra. So three different standards suites that are all covering, for example, geotechnical information, and we can include digs in that. So there's a process of determining the overlap, determining how to increase the overlap so that we are able to integrate as much information from these different perspectives as possible. So really, these means are taking different perspectives, but figuring out what contributions contribute to an integration of particular use cases. So use cases in this original study, there were 6 of them, starting from excavations and then looking at other really compelling needs for integrating information about the underground. There's emergency response that shades from response into maintenance, so trying to avoid as well as mitigate emergencies. And then some larger, longer-term perspectives, reducing the cost and risk of large-scale construction by incorporating the underground into designs for construction. And then disaster planning, really not just responding, but saying, okay, if there's flooding, what will be affected? If the electricity goes down, what other utilities are being affected? And how can we improve not only that resilience, but the normal operation of the infrastructure that is supported by underground structures. So there are many useful data perspectives that affect that, from the simpler harmonization and integration to really looking at how we can examine what's there and what it does, and how we can actually work with it. And that's many times going from the construction perspective, represented by IFCs, or the ownership perspective, represented by land infra, to the simulation and prediction, represented in many cases by city GML models and similar constructs. So trying to get these different data perspectives out of the different community perspectives that can feed into it, make it a big task that really has to be taken in increments. So how do we build such a model? So one of the aspects of this is that we have different needs, and those needs require different levels of complexity and coverage. And so patterns that enable modularity and extensibility are really important. Just looking at the asset perspective, what do you have there, doesn't require much detail about uh, those structures and how they work together. The excavation, what will I hit, requires detailed two-dimensional extent, not as much three-dimensional extent. So how do we enable that sort of increasing detail, capability, and coverage? So there are three main methods of doing this. So the first is the goal of interoperability. That's the harmonization. So we can say once we have a model which covers the common concepts, we can enable interoperability of those concepts across different data sources. We can look at specialization. So those blue arrows saying, well, we have something which is an object. Now we have something which is an object in a network. Now we have more information for specialized use, talking about what kind of electrical network component it is. Of course, every time we specialize, we add more without subtracting. So another method is adaptation. We add modules, literally interfaces that say, at this level, we're interested in the 3D properties. In the middle, we're not so interested, but in getting to a specific component, again, we're interested. So we can add on that additional capability where it's needed and where it is not. And then when we're talking about networks, there are some use cases for which that's not important. Whether these two pipes are connected together is less important than are they rusting out and will I hit them? But for dependencies, for operational concerns, then how the network is connected and what it serves becomes very important. So those relations added on separately become critical to an effective model. So being able to have model profiles that add just those elements that are needed for which data is available is very important for an effective integration model. So here's just a brief look at the model that has been developed over the last couple of years, the MUDDI, Model for Underground Data Definition and Integration. So we have core objects, we have specializations into network objects, containers and supports, environmental regions. We have these additional capabilities. So capabilities to take data in from surveys or sensors, capabilities to send data out to CityGML, to IFC, to asset databases, and then additional capabilities such as network graph or supply regions for network segments. So each of these can be added on in an implementation of MUDDI to suit the particular purpose and data needs of a particular use case. This is a quick look at adding some of that complexity. So here's an example of having a node network. And for many purposes, it's not so important to know what additional detail is hidden in that node. But this graph node interface enables that detail to be added. So a particular case in the middle, graph node 2, is here's a pump. The pump moves water through this water network. The pump is powered by this node on the electrical network. And so for dependency and operational simulation, you really need to know that there's in there. For other specs, you don't need that information. So this is also an upgrade path to a particularly capable but complex utility network model that's associated with the AGML. Okay, so having these different levels of model, what can you do with them? And so this is where the integration model really comes into its own by supporting different system architectures. So being able to take information from a variety of themes or industries or types of networks, commodities, and then providing different levels of integration, assets, or just structures, or full networks, or really functionality, and address different applications. And these can be full integrations, but generally that's problematic to harmonize with the operations of the individual utilities. What's much more effective is to have a federation approach where the data providers have a contract to provide just the information that's needed in the common form when it's needed, and a information system provides that on demand, or perhaps in a cached form, or as a updated repository where testing for data quality and completeness can be done.
Josh, thank you very much. I appreciate that. We're going to cut you off because we're running out of time, but we really appreciate that. And we do have one quick question for you. Do you have kind of an aha moment where, or a kind of a story that people can really understand where that true benefit of the integration is?
So we had so Lisbeth will talk more about that. I'll just tell a quick story about the importance of a variety of data. So we're engaged in this project with Ordnance Survey to find out what data is available for utilities in Northeast England. And going through, well, here's the pipes and here's the other thing. And then there was this other record. And we said, well, what's that? Well, that's not important. That's not one of the utilities. So, well, tell us what it is. Oh, that's a record of unexploded ordnance.
All right, thank you very much. I think that makes the point really well. So thank you.
You're welcome.